Varieties. Today we will concentrate on compactifications. Can you hear me in the back? Yeah, is that okay? On compactifications of additive groups. So this is just to remind ourselves of what's happening. So we work over a number of fields, and G in today's talk will be a unipotent group. So upper triangular group, or Heisenberg group, or just the additive group. So additive group, just affine space is a space, but in the standard vector addition on it, over F. So we look at the representation over F, so some polynomials there. PGLN plus 1 acts on Pn, and then we have a standard height on Pn, and we take a point in Pn and look at the orbit through this point and count points on G mod H, where H is a stabilizer of our point of F, height less equals than B. Now already I'm skipping over this little issue whether G mod H of F is the same as G of F mod H of F. Well, this is not the case in general, but let's not worry about it for now. In the examples we look at, it's not an issue. And it was asked last time, we discussed it, well, how does it depend on X? And so how do we understand these varieties? The main difference between what we saw yesterday, the toric case, and what we're going to see today is that, well, semi-simple groups like tori, the representations don't admit moduli. So they're rigid. So they are sort of classified by these rigid combinatorial objects, and we saw them on the board, these fans, polytopes, and so on and so on. While groups like unipotent groups, well, the representations deform. And in fact, so this is a standard example of what we look at. Just take two commuting matrices in PGLN plus 1, so that's like GA squared sort of put in. And then if you want to classify all those representations, well, the sub-problem will be to understand, all pairs of commuting matrices, and it's known to be a wild sort of classification problem, moduli problem. So there is no, sort of algebraically, there is just no language or no scheme to classify these representations, and correspondingly, no scheme to classify varieties which occur. So the closure of the orbit through a point is an equivariant compactification of G mod H with, well, a G linearized very ample line bundle L, so that's our projective embedding. And then putting a height on Pn gives an adelic metrization of the line bundle. So we want to count points, we want to understand asymptotics of points of bounded height, but this time we cannot reduce this to some combinatorial data as yesterday. So yesterday we saw, well, these are these combinatorial data, and we proceed by sort of using this combinatorics. So here is an example of an equivariant compactification of the additive group. So take Pn, well, it's a compactification of the affine space An, so there is a Pn minus 1 in the boundary. Now take anything you like in that boundary, in any subvariety of Pn minus 1, and blow up Pn with center in this subvariety. So it turns out that the Ga to the n action, the standard action on Pn, will extend to an action of Ga to the n on this blow up, and that's an example of an equivariant compactification of Gan. So if you take Ga squared, so you have Ga squared in P2, we have this line, P1. So pick any number of points on that P1 at infinity and blow them up. And so what are the moduli in this picture? Well, it's the moduli of points on P1, so n points on P1. So already sort of interesting moduli. And if you take P3, then you can pick any plane curve at infinity, blow that up. So the moduli are the moduli of curves, any degree, whatever you like. And so as you can imagine, basically any variety that you can realize, any variety in Pn minus 1 will give you some compactification, equivariant compactification of Ga to the n. And so that's the issue we are fighting with. So this is just one way to visualize sets. We tried to classify these GA equivariant varieties in dimensions 3 with Professor Hassett, putting some restrictions on the boundary, and it's very interesting geometrically, but the picture is not at all complete. So even in small dimensions and with restrictions on X. Anyway, so this is our unipotent variety. We have a unipotent group G and an equivariant compactification. So while we don't understand the moduli, we can still say something about the geometry. And so the geometric invariants of interest to us are, well, the Picard group, and this is how you get it, as described. Take a divisor, push it to the boundary, it becomes the sum of boundary components, and the relations come from functions on the complement, and the complement is just the affine space, a unipotent group, so there is no such functions except constants. So the Picard group is freely generated by the boundary components, their classes. Now the anti-canonical class can be written as a linear combination of boundary components with some coefficients, and it turns out that in the case of toric varieties, it was the sum of boundary components with coefficient 1. So now here all the coefficients are bigger or equal than 2. And the effective cone is just a simplicial cone spanned by well, the boundary components with no negative coefficients. And while the geometry is complicated, the invariants are easy. As you saw yesterday, for toric varieties, effective cones can be anything you like. So here, the effective cones are simplicial. And so that was one of the hopes why we thought that maybe some version of the minimal model program in dimension 3 will help us to understand these varieties. The anti-canonical class is not necessarily ample. So that will lead us to the Fano case. And as I said in the second lecture, I think the Fano varieties in dimension 3, there are finitely many families, like on 100 or 120 or something. So here, the anti-canonical class is not necessarily ample, but it's effective with coefficients bigger or equal than 2. Then we thought, oh, maybe we can push this algebraic geometric classification, and it leads to many interesting concrete problems, which I cannot discuss right now. But for our counting purposes, we need heights, all right? So local heights first with respect to the boundary divisors. So you look at H0 of di, so it's G linearized, and as you know, a unipotent matrix can be brought into upper triangular form. So there is one section that's invariant with respect to the action. And then and metrized line bundle means that, well, at each point, if you have a section non-vanishing, so you have the notion of a norm of a section at this point. Okay, so, and the height is a norm of this distinguished section. And the height globally is then the product of its local heights. So this is well defined for x in G of Fv and x in G of the Adels correspondingly. And then just as yesterday, we get a height pairing between the adelic points of the group and the complexified Picard group to C. And so how do we do it? Well, take an x here and the sum of boundary divisors with some coefficients. And now again, a priori you could say these are integers or complex numbers. So we will use complex analysis, and so this Sj, that kind of generalized heights. And if you restrict to integers and rational points here, then you get really a height with respect to, say, a very ample line bundle if you pick a very ample class here with respect to some metrization on that line bundle.
I'm sorry, I don't understand. So Fi vanishes on Di.
It vanishes on Di, but Di is in the boundary. So it's okay if we look at the complement of the boundary. So we have to evaluate this at points in the complement of the divisor, of course. Yes?
How do we relate to the points on the divisor?
Oh, well, that we don't, I mean, of course you can define the height on rational points as described. Take a line bundle, take maximum of the coordinates in this embedding. But I want to have an adelic height on the Adels, And so for that, I have to stick to the complement, It's G, it's not X. Yes, please.
Why the boundaries are always the union of divisors?
Sorry?
Just one.
Why is the boundary union of divisors? Well, the X. Why is the boundary union of divisors? Well, so you're thinking about the setup we had in the beginning. So take this representation and just look at the closure, yes? Now, the thing which I should say right away is that, all right, the compactifications can be very singular a priori, yes? But for our counting purposes, we can always reduce to smooth varieties, and in fact, we will also reduce to the case where the boundary is actually a divisor with strict normal crossings. So the way it works, you take resolution of singularities equivariantly, so with the action of the group G. Now, of course, when you blow up the variety, everything changes, the pK group may change, and things change, but we have the functorial formalism for heights. So we restrict to the risky open subset, to the open subset, the group G and rational points in G. And the pullback of a line bundle from the singular variety to the resolution of singularities, well, the height of a point in G with respect to L downstairs is the same thing as the height of the preimage, so to speak. So after all, it's an isomorphism on these subsets G with respect to the pullback of the line bundle. So one thing we will sort of assume for our proof right away is that the variety X is smooth and boundary is a strict normal crossing divisor. All right? So that's the first geometric simplification which will help in the analysis. All right, so we have this height, and we can sum over all rational points in G of the height, and here again with vector S in the complexified pK group to the -1. And the Poisson formula says, okay, we can, I write Poisson formula, but in fact, I'm also looking at general unipotent groups like Heisenberg group or just the upper triangular group. And in general, we may even have infinite dimensional unitary representations occurring in this space. But there's always one representation in the spectral expansion that's sort of relevant and of interest to us, and that's the trivial representation. So I write down the contribution from the trivial representation, and then there will be a tail which we'll have to analyze. Now, in case G is additive, so a product of GAs, of course, the only representations we'll see are characters. All right? But again, for the Heisenberg group, there is a whole series of infinite dimensional representations that have to be analyzed. So this is kind of a generalized Poisson formula in the unipotent case, and we apply it in the case of GA to the n. So here is the picture. Sum over the function over the rationals is, well, contribution from the trivial representation, and sum over all non-trivial characters of the Fourier transform. So here is sort of the Fourier transform. Again, you have to sort of think a little bit about the normalization of the measures, and then you sort of want to analyze the Fourier expansion just like you work with Fourier series. Now, for that, or before we start doing this in the full generality, let's look at the case of A1 sitting in P1. What is our local height function? Well, we have a coordinate x on GA, and so we just take maximum 1 and the p-adic value of x at non-Archimedean places, and then, for example, square root of 1 plus x squared at the Archimedean place. So the zeta function, and of course it is what we had before, like in the toric case, you would have picked, again, maximum 1 absolute value of x. But here we'll be doing, we'll be working with sort of Fourier transform of the height at infinity, and already I should say that, well, when you do Fourier transform and you have functions which well, are not very smooth, then it begins to mess up the Fourier side, and it's going to be difficult to get estimates. So it's better to work with so-called smooth metrizations at infinity for these kind of analytic purposes. So here is a height zeta function, and so we have the contribution from the trivial representation, and there's a sum over all characters. So let's compute with integral over the adels. So it's GA of AQ. All right, so we have the following domains. Where does this function change? Well, we have x being less equal than 1, and then the function is just 1. And so we're integrating 1 over this domain. And then we look at where the value of x is fixed, and it's p to the j, and j is bigger or equal than 1. And now the volume of this domain is this, p to the j minus p to the j minus 1. Right? We have this stratification. And then we just need to sum a series. So here is the height integral, and this is what we get from the domain u0. So it's just 1. And at the others, this is the height, p to the minus js, and this is the volume, and then you sum it up, and this is what you get. All right? So quite straightforward. And at the infinite place, well, we don't need the exact value for that, and I hope I didn't make mistakes computing this integral, but whatever it is, it's convergent, it's a function in S, and that's it. Now we need to look at the characters. So how do we think about characters? Well, QP mod ZP, it's like sort of this tail, A over P plus 2 over P squared, so on and so on. It's sort of finite in this direction, so we may as well embed it into Q mod Z. And so this is a character. Now this is understood as something in Q mod Z, this, and then you have E2 pi times this, and AP is in QP. And we'll be mostly interested in unramified characters, so trivial on ZP, so AP and ZP, for a reason I will explain later on. And then at the infinite place, well, we just have the standard thing. So the global character is a product, and there is this A, and we are sort of taking a component of A's of A in the various at the various places. So we have local dualities, and we have a global duality. Somehow AQ over Q star, so the characters trivial on Q are well labeled by Q. So now unramified for all P just means that A is in Z. So if you have a character trivial on Q and unramified, then the corresponding A is in Z. And so in the high-dimensional case and over general number fields, it's quite similar. So you have to take somehow trace to get from F to Q, and then if you have several components, then you just take a scalar product of the corresponding things. And then we need to compute the local integral for the non-trivial characters. And we realize that, well, A is an integer, so we look at the unramified situation. Then we have some primes which are sort of bad. When P divides A, then you begin to see some difficulties in these exponential sums. But when P doesn't divide A, when P has nothing to do with A, then there is sort of a clean formula, and for all those P, this is what we get. So when we put these together, we see that the zeta function of P1, the height zeta function, well, so that's a trivial representation, and then we have a sum over all A and Z. So now I should say Y, all A and Z. Remember, the height function was maximum of like 1 and absolute value of x. And it's invariant under translations by ZP. So when the height is invariant under the compact subgroup ZP at all places, well, then all the characters which are non-trivial on that compact subgroup, well, the integral of the height against these characters is going to be 0. So it's again the same story. Therefore, the invariance of the height with respect to the compact subgroup forces the characters to be unramified. And so when we look at the formula, Poisson formula, so we're summing over the rational numbers, something, then we get, this integral, and we get sort of a dual, the sum on the dual side, and the beauty is that, a priori, we would have, using that, like, say, Q or F are self-dual. Here is the sum over the rationals, and here is the sum over the rationals. So what have we gained? Well, what we've gained is that the invariance of H with respect to a compact subgroup, which is going to be a general fact, forces the vanishing of Fourier transforms for all ramified characters. And so rather than summing over the rationals here, we begin to sum over a lattice. And in the case of P1, so rather than summing over Q on the spectral side, we are summing over an integer. And so the summation here is over the integers, not equal to 0, because 0 is a trivial representation of, what we've just computed. And we've computed these local factors for P not dividing A. And for P dividing A, we have something which is quite difficult to compute, because, then we have to see, does P squared divide A, P cubed, and so on and so on. It's doable in the case of P1, but it becomes very impractical in higher dimensional situations. So we have an integral of the height times the character, and we're just going to replace this by its absolute value, and the absolute value of the character is 1. In other words, at those finitely many primes, we're just going to write down the integral similar to the one at the trivial representation. Okay? So, and then we'll estimate the contribution from those primes, there are finitely many, and then we still have the contribution at infinity. So here we have this sum. Now it's a very complicated way of counting points on P1 over Q, right? We know what the answer is, Z squared, and then there is like 1 over zeta 2. So let's see whether we regain this information from here. So where are the poles coming at the trivial representation? Well, the poles are at S equals 2, right? So, and the pole, the residue at this pole is 1, and over zeta 2. And then at S equals 2, you get something here, and it's, of course, the volume of the ball, right? So we took the height to be square root of 1 plus x squared. So that gives you a certain sort of unit ball. And so that's the volume of the unit ball. And that's sort of the contribution from the Archimedean component. And now we need to see what's happening here. Well, each term on this side is holomorphic in the neighborhood of s equals 2. So there are no problems here. So this is bounded by constants for P divides A. And now each of these terms is holomorphic and bounded, but we still have to sum infinitely many of those. And so how do we do that? Well, the way you would do it in Fourier analysis, you do integration by parts. So there is some character missing here. So there is some more stuff hidden. Sorry, we went overboard somehow, but I wrote it down here. So the contribution from here, well, you bound it by the trivial representation, so here is an absolute value. And S of A, those were the primes dividing A, and basically you just look at, well, there are finitely many primes dividing A, and then there are constants from each of those primes. So there is something which you can estimate probably 1 plus S of A to the epsilon. It's not significant, but it depends on A. Now, to get convergence of this sum, we need to do integration by parts, like you do in Fourier analysis. So this goes into here, then you take the derivative of that, and it turns out that for S in the neighborhood of 2, indeed, what's left, it's going to be convergent. But integration by parts puts 1 over A into the denominator. So, and if you do integration by parts many times, you can pick up any power of A in the denominator, any power you like. And so you get some estimate, well, some number n, as many times as you take integration by parts, and then 1 plus norm of a to the n, and certainly that will be enough to beat this term and to ensure convergence over all such a's. All right, so this is P1 in a complicated fashion. So what do we get? The trivial representation gives the expected pole at s equals 2, and now we recall that the anti-canonical class for P1, after all, it's O2, so that's a 2 that shows up. And the leading coefficient at this pole is a product of local densities. After all, it was an integral of the height function over the Adele, so it's a product of all these local integrals. And so then we have it in front of us, so product of local heights times dx, and what could it be? And we identify this Tamagawa number defined by Peire. That will, the discussion of these Tamagawa numbers will happen next Tuesday in more detail. So now we look at the general case. So here we have some complicated equivariant compactification of a unipotent group, G, and we look at its the v-adic points here, and now so we're going to integrate the height function against, well, over GFV. But it turns out that the way to analyze these integrals purely geometrically. So yesterday we had this fan on the board, like for P1, if you remember, and we said, well, let's compute the height integral locally. So the height was this q to the piecewise linear function, and then we had this sum over all cones plus minus, a purely combinatorial thing. So now we're going to have a geometric way to compute these height integrals. So for that, we again assume the boundary is strict normal crossings. We look at the stratification of the boundary by intersections of these divisors, and then we look at open subsets. So boundary is something like this, and so this is the divisors di, and so then they intersect, and then the di are sort of di's minus all the intersection points, and then it sort of continues into higher codimensions, and it's a disjoint union of sets like this. So the v-adic points, we have a projective varieties, well, same thing as the OV-adic points, and OV you can reduce mod v, and you get points in FQ. Those are just finitely many, and those finitely many points, they will lie in one of those strata. And so when you take the preimage of a point lying in a stratum like this, you get some domain here, and we will break up the height integral as a union or as a sum over integrals over all these domains. So that's the goal. And there's a closed formula. So this is the formula. You take the height, integrate it over here, and then what you get is a union over all strata of the boundary of, well, the number of FQ points in each stratum over Q to the dimension, and then you have this product over I in here, Q minus 1, QS minus kappa, where kappa, just as a reminder, is a coefficient at the divisor di of the anticanonical class. So the anticanonical class was sum of kappa i's di's, and that's the kappa that shows up here. Now with Si, again, I work with distinguished bases in the Picard group. So my basis boundary component boundary divisors di. So that's what we get. And then you can draw conclusions about the shape of the corresponding global product. So let me, so I think we have time, write down at least a sketch of this formula, a sketch of a proof of this formula. So this is how it works. So we have GFV sitting in xfv, and that's xov, and that's in fq, and that is a union of its boundary strata, fq. So we have finitely many points. So we pick an x, sort of a reduction in here, so it will fall in one of those strata. Now we look at local analytic coordinates around this x in here. So, or rather, well, in the reduction -1 of x tilde, so x, we have coordinates like this. So xi, where I is an I, and then the product over yj's, where j is an j, and I union j, well, that's the set of all indices we have here. So, so maybe I is in this calligraphic I or j calligraphic. All right. So now, so what are the properties? The properties are that the divisor di is locally, so defined by the vanishing of this coordinate xi. And then, well, so we do change of variables. We go into, well, it's like a partition of unity, if you like, in the real case. We go into the neighborhood of this point. We change coordinates. Our integral is with respect to measure dx. But when you change the coordinates, you find that, so dxv is then a product. So there is sort of a Jacobian coming into play. So product over I in I, q, and here comes kappa I, valuation of xi, and then the product of the dxi, now these are these i's, I in I, product of dyj's, j in j. So when you do, like in real analysis, change of variables, so you determine, like you have like Jacobian matrix. You take absolute value of the Jacobian matrix, right? So this is the same thing. But, so what's the Jacobian matrix? So this is exactly the canonical class that's in there. And so we need to look at the multiplicity of the corresponding thing along the divisor di. And so the valuation of xi comes into the game. So it's like we have sort of tubular neighborhoods around di, and we're going to integrate the height function with respect to this new measure here. So the integral over this space -1, so h of x s -1 dx, well, it's going to be an integral over, well, we already fallen into the neighborhood at the di's, so to the I, so product I in I of these kind of expressions, so q to the kappa I, valuation of xi, sort of dxi, and now we need the height function. But the point is that in local analytic coordinates, the height function, the v-adic height, is nothing but the distance to the boundary v-adically. So in other words, locally, the height is simply the v-adic value of xi, and we are interested in the height to the power si. And the outcome is that since we are so q to the minus si valuation of xi, the height to the -1. And then we have the others where we integrate over ov, so j and j, integral over ov, and then we just integrate 1. So the coordinates d, y, j. So this, so mv still, mv, I think. So this integral will contribute 1 over q to the number in J. And so this integral, well, it's a product of geometric series as before, just like we did it for P1. Remember, except that there are these shifts happening. So this gives us a product over I and I, well, Q minus 1 over Q to the Si minus kappa I plus 1 minus 1. And then we pull everything together, we're summing over all points in the strata, and that's a formula that's written here. So each sort of X contributes this, and then we sum over all the strata, we have that. So this p-adic integration is extremely powerful because, well, so here we integrate a height function over a group. But we are getting information. We're getting information over, well, the number of points, for example, on X over the finite field FQ. Just by putting Si equals kappa I, so these terms disappear, and then we have a sum over all strata of the number of FQ points in a stratum over Q to the dimension. Well, that's exactly the number of points in X over FQ over Q to the dimension. Now that is sort of a very fruitful observation, and a similar observation led Batarev to his theorem about Calabi-Yau's birational Calabi-Yau's having sort of the same Hodge numbers, something like this, exactly from this kind of like p-adic integral computation. So you show that on the risky open subsets you're integrating the same thing, and therefore the integral of local heights, so to speak, will give you FQ points, and then you get it for many, many Qs. So using the Weyl conjectures, you get some statements about cohomology. So, and then it just took off because look at these integrals. So X could be singular, for example. Now, the integrals we are looking at, they then become sort of invariants of these singularities. So you can understand singularity by means of p-adic integrals. And then you can push it further from p-adic integrals. You can make these motivic integrals. And then there is all this development, all the work of Deneuve, Lauder, and then it sort of really explodes in many, many different applications and fields. But for our concrete purposes, we look at the Euler product. So we have the local factors, and pulling together the Euler product, we just need to understand, well, what are the leading poles of this function? So let's look at this. If you have at least two, if I has at least two elements, that is, if you're looking at an intersection of at least two divisors, maybe more, then the number of FQ points in that variety, well, it's Q to the dimension. So if the dimension is, well, dimension minus 2, then you see 1 over Q squared. 1 over Q squared. And remember, analytically, we are interested in Si being close to the canonical class. So close to, so Si close to kappa I. And then you see that these contributions, like 1 over Q squared and this, they just factor out and become sort of a convergent Euler product. Now the main poles, they will come from I's consisting of just one element, divisors. So we would have a divisor, one of these di's, and then we count FQ points on divisors. So as I told you, these boundary components, divisors, it can be anything you like. You look at this y, you take a blow-ups, then you get a component which somehow knows about this y and FQ points on y. But in fact, we don't really need to know everything about this FQ points. All we need to know is this Q to the dimension minus 1 and 1 over Q, and then the rest of that will go into the tail, will go into a convergent Euler product. Now, of course, we will need uniform estimates on whatever that rest is. But for now, if we just put 1 over Q here and keep track of these things, then regularizing with the Euler product from these contributions, we just see product over zeta function over I from I in our index set. Zeta functions shift Si minus kappa I plus 1. So that's what we get. Times this function, which is holomorphic in some neighborhood of kappa I. And so this is a shift of the cone of effective divisors, just given by Si bigger or equal than 0, by the anti-canonical class, which is, well, kappa I, sum of kappa i's. And this trivial representation produces poles along the faces of the cone. And the pole of highest order, of course, will be given where all of these have poles. That is, when all the Si are equal to kappa I. So that's the picture, and maybe I should draw it one more time. So the outcome is that so here we have a simplicial cone. So S1, and so it continues. And so here we have this shift by minus kx, so kappa I. And we've identified poles from the trivial representation, and pole of highest order is right here, and its order, if you restrict to the anti-canonical class, its order is exactly the rank of the Picard group. And so the height zeta function already has poles in this trivial representation. But we are not done yet, because we have to analyze the rest of it, so the tail. So what happens with the characters? Well, the character then on GA to the n, well, it's going to be a linear form like this. And, well, I think about this A as being, well, say, over the rationals, A. And then I look at A bracket with X. So it's A1, X1, A2, X2, and so on and so on. It's like a linear function on GA. But now we live geometrically. So with GA to the n, it sits on X, and that this linear function just becomes a rational function on X. And it has a divisor. So there will be a divisor. And so here are some boundary components. But now, always the I have to be bigger or equal than 0. So why is that? Because we proved that the cone of effective divisors is spanned by the boundary components with non-negative coefficients. So this is effective. So these di's have to be bigger or equal than 0 for all i's. So we have to look at the behavior of these functions fa as A varies. So A is going to vary over lattice. So that's coming from the invariance of the height function with respect to the compact subgroups. And just as before, there will be a set of bad places, those where this linear function begins to behave badly, like some of the coefficients are then divisible, not V, and so on and so on. So there will be finitely many places depending on A which will exclude. And then let this be the set of all those indices where the di of this FA is just 0. Now, it can't be 0 throughout. So this is really a proper subset of the set of all indices, because if you had zeros throughout, well, then there wouldn't be any zeros, but clearly this has zeros, right? So it's, after all, for A non-trivial, it's really a non-trivial function, so it's got to be zeros and poles. And then there's a formula which is very similar to the formula for the trivial representation, and is derived in a similar way, which says that the Fourier transform with respect to this non-trivial character is a product over all i's in this subset of I of zeta functions times a function which depends on A and which we will have to bound uniformly in some sense, times the contribution from the places at infinity, the Archimedean integrals. And then Archimedean integrals, they are sort of similar to what we've done for P1. There are more complicated expressions, of course, geometry is in there. They're computed by means of partition of unity, just like we did in the p-adic case, except that it's, well, really analysis partition of unity. Now, let me show you the differences between that integral for the trivial representation and now the integral of the height with respect to characters. So EA is somehow the zero divisor of, so it's where AX is 0. Now, So we have something resembling a principle of stationary phase. If the bracket AX is 0, well, then we are integrating like a trivial representation, so to speak, yeah? And so we have the height times kind of a trivial representation dx. But the set of those x here, where AA is 0, well, it's in higher codimension. And so, yes, the height integral somehow localizes along with divisor EA, but the trivial representation will still dominate in the analysis, simply because in the p-adic integral and in the Euler product, we have, well, here it's a proper subvariety, fewer points. And so this is the exact formula for that. You can actually see what happens. So the main difference in the integral is that here you still have a character, and you would have to introduce local analytic coordinates not only along the strata coming from the boundary, but also all the intersections of this EA with the boundary strata will have to be addressed separately. So in addition to this fixed boundary, you have this varying divisor of EA. And, now, as we are going to be summing over the A's, we need to have uniformity in all these local integrals, and that's a big issue. And that's this estimate, which I write down here. We can get a bound of 1 plus a to the epsilon for this function. That's a polar set. And then again, integration by parts will give us convergence of the spectral side of the height theta function. So that's our trivial representation with a pole we expect from predictions, and we are happy to see. But for each subset of sorry, this is a wrong I. This is not a calligraphic. It's this I, strict I, and this is also the strict I. Then we have a sum over all subsets of this calligraphic I, of this I belonging here, of this zeta function, and then this function f tilde I of s, where so we have to look at all characters with the property that this I0 of the character is exactly this I. So if you look back at the formula here, the Fourier transform, it gives, well, some I0 of A, which is a proper subset. And now we're just going to put together all I0 of A's. After all, these are just subsets. So run over all subsets of these indices, and then look at all characters with the property that, well, I0 of A is this subset. So that's what's written on the other side. All right? So in other words, these also contribute to poles. Well, the poles in the neighborhood of the anti-canonical class, they have slightly smaller order, strictly smaller than the whole set. So let's see. I'm going to go up. So that's our picture. In the neighborhood of this point, the pole of highest order comes from the trivial representation. But if you look in the neighborhood of other points, and that would correspond to picking other line bundles, other than the anticanonical one, then we see that there are other poles showing up from other characters. Now, what we will do is we pull together all these other characters. It turns out that they form a subgroup in the group of characters. And then there is another Poisson formula which comes into the game, which will show that the corresponding constant at this pole is in fact coming from, so constant is, well, when we do Poisson formula one more time, we realize that it's going to come from a certain vibration, which, well, maybe n tilde, with n tilde, and this is sort of the group X sitting in X in the rational points of Y of some integrals of height functions again and again, And these integrals, again, can be identified with Tamagawa numbers of fibers of the fibration, which is just coming out from the analysis of this formula. So it's sort of very instructive to see this interplay between geometry and analysis. So if you didn't know any geometry at all, you just wanted to compute these local and global integrals and analyze the height zeta functions, then so this is what you get. And then you try to say, well, what does it mean on the geometric side? And on the geometric side, it means this. And then you sort of read about these versions of the minimal model program, the Fujita version of the minimal model program, and you identify the answer with what the prediction would be from the minimal model program. Yes, that's it from my side. So you've seen a whole other class of varieties treated analytically, and on Tuesday next week we will discuss integral points and also these Tamagawa numbers, which we are sort of present sort of in our discussions all the time, but which we haven't yet formally defined. Thank you.